Assalamualaikum and hello to everyone. In this video lesson, we will continue with chapter 4 of our syllabus. In this video lesson, we will still be covering the third subtopic as highlighted on the left. For this video lesson, we will look at the Rankine cycle under actual conditions. The objective for the subtopic is on the right of the screen. In the previous video lesson, we have seen on how to analyze the Rankine cycle under ideal conditions. However, for actual cases, due to irreversibilities that happens in the pumps and turbines, it is necessary to consider the isentropic efficiency of these devices. This is the example for a TS diagram under actual conditions. Now, we have covered the topic for isentropic efficiencies in the previous chapter. Therefore, these equations should not be new to all of you. Just a quick reminder that for actual conditions, we will use the subscript A, and for ideal conditions, we will use the subscript S. And it is also important to know which component should we consider its isentropic efficiency. For pumps, in order to calculate the isentropic efficiency, we must know how to calculate the amount of work input based on ideal and actual conditions. For turbines, in order to calculate the isentropic efficiency, we must know how to calculate the amount of work output based on ideal and actual conditions. Now, let's look at an example for Rankine cycle under actual conditions. You can pause the video to read and understand the question properly. Now, please take note that for this question, only the turbine has its isentropic efficiency. Therefore, at the pump, we will consider it to be under ideal conditions. For step 1, please try to draw and label the schematic diagram for a Rankine cycle. For step 2, to calculate the rate at which heat is added, we can use the following equation. To find for power input, we can use the work input equation for ideal conditions. To find for net work output, it is simply the actual work output minus the ideal work input. And finally, to find for thermal efficiency, we can use the following equation to determine the cycle's thermal efficiency. For step 3, as usual, find the required properties at each of the state. For state 1, based on the given information, we must read for specific enthalpy and specific volume here at state 1. Now, specific volume is read because it will be used later in state 2 to find for the ideal work input. At state 2, to find for specific enthalpy, we need to calculate for the ideal work input first. And then we can solve for specific enthalpy at state 2 by using the following equation. At state 3, using the given information from the question, we can read for the specific enthalpy at state 3, and since this question involves the isentropic efficiency at the turbine, we must also read for specific entropy in order for us to calculate the ideal condition later in state 4. At state 4, solve for the ideal conditions first. Using the appropriate table, we must check for the phase of the substance. And as we can see, since the phase is a mixture, to solve for ideal specific enthalpy at state 4, we will use the equation for mixture. For actual conditions, to find for the actual specific enthalpy at state 4, we will use the isentropic efficiency equation, and solving this equation, we will be able to calculate the actual specific enthalpy at state 4. Now, remember to also check for the phase for the actual condition. in order for us to draw the TS diagram correctly. For step 4, now substitute and solve for the question. Now, depending on the decimal points, okay, the amount of decimal points taken during calculation, some of your answers might be slightly different from what is shown in the video. Do not forget to sketch the TS diagram based on the face of the states, okay. If there are any questions regarding this example, please do ask me. Do not hesitate to ask me. So, we have come to the end of this video lesson. We will continue with the next Rankine cycle, okay, in the next video lesson. Thank you for your attention and have a good day.